Hey friends, welcome to the YouTube channel all about electronics. So in this video we will solve some problems based on the transient analysis for the first order RC and the RL circuits. So in the last couple of videos we had seen that how the basic circuit components like resistor, capacitor and inductors behave during this transient. And then after we have derived the expression for the first order RL and the RC circuits. So let's quickly revise what we had seen in the last couple of videos. So we had seen that inductor opposes the instantaneous change of current. So let's say at time t is equal to 0, if there is no current flowing through this inductor and suddenly if some voltage is applied across this inductor, then this inductor will opposes the instantaneous change of current. That means at time t is equal to 0 plus also the current that is flowing through the inductor will be 0, or we can say that the inductor acts like a open circuit, and at time t is equal to infinity it will act as a short circuit. Similarly, at time t is equal to 0, if some current I0 is flowing through this inductor and suddenly if the source is disconnected from that inductor, then at time t is equal to 0 plus also the current I0 will continue to flow through this inductor, or we can say that at time t is equal to 0 plus this inductor will act as a current source with a value of a I0, and at time t is equal to infinity this inductor will act as a short circuit. Similarly, we had seen that capacitor opposes the instantaneous change of voltage. That means at time t is equal to 0, if there is a no charge across the capacitor and suddenly at time t is equal to 0, if some voltage is applied across this capacitor, then this capacitor will opposes the instantaneous change of voltage. That means at time t is equal to 0 plus also the voltage across the capacitor will be 0, or we can say that the capacitor acts as a short circuit. While at time t is equal to infinity or in a steady state condition, as the capacitor will get charged up to its full value, then it will act as a open circuit. Similarly, at time t is equal to 0, if there is some charge across the capacitor and the voltage across the capacitor is, let's say, V0, and if the source across that capacitor is removed at time t is equal to 0, then at time t is equal to 0 plus the capacitor will act as a voltage source, and in a steady state condition this capacitor will act as an open circuit. Then after we have derived the expression for the RL and the RC circuits. So here are the few steps to solve the transient problems for the first order RC and the RL circuits. So first, draw the circuit at time t is equal to 0 plus. Then after, find the initial conditions in the circuit. That means the capacitor voltage at time t is equal to 0 plus if it is a RC circuit, or find a inductor current IL at t is equal to 0 plus if it is a RL circuit. Then after, if circuit contains more than one resistors, then find the equivalent resistance of the circuit. Similarly, if the circuit contains more than one inductor or capacitor, then find the equivalent capacitance or equivalent inductance for the given circuit, and the time constant for that circuit can be given as R equivalent into C equivalent if it is a RC circuit, and if the circuit is a RL circuit, then the time constant can be given as L equivalent divided by the R equivalent. Then after, find the value of a capacitor voltage or inductor current at time t is equal to infinity, and the total solution can be given as final value plus initial minus final value into to the power minus t by capital T, where the capital T is nothing but a time constant of the circuit. So the inductor current can be given as ILT, that is equal to IL of infinity plus IL of 0 minus IL of infinity into e to the power minus t by capital T, where this capital T is nothing but a time constant of the circuit. Similarly, if the circuit is RC circuit, then the capacitor voltage can be given as Vc of t, that is equal to capacitor voltage at steady state or at time t is equal to infinity plus capacitor voltage at time t is equal to 0 minus capacitor voltage at time t is equal to infinity into e to the power minus t by capital T, where here this capital T is nothing but a R into C. Now these equations are valid when the excitation that is given to the circuit is a DC excitation. So using this equation for the first order circuit, we can find the voltage or current across any element during this transient. So now let's solve some problems based on these transients. So in the first example, we have given that the capacitor voltage is 0 at time t is equal to 0. And we have been asked to find this capacitor current ICT for a time greater than t is equal to 0. So we have given that the initial voltage across the capacitor is 0. That means Vc of 0 minus that is equal to 0. As we know, the capacitor opposes the instantaneous change of voltage. So at time t is equal to 0 plus also, the voltage across the capacitor will remain 0. So first of all, let's draw a circuit for the time t is equal to 0 plus. So at time t is equal to 0 plus, this capacitor will act as a short circuit. And as this capacitor gets short, so this 20 kilo ohm resistor will also get short circuited. So at time t is equal to 0 plus, the equivalent circuit will look like this. And hence the capacitor current IC 0 plus can be given as 10 volt divided by 20 kilo ohm. That is nothing but 0.5 milliampere. So this is the initial current at time t is equal to 0 plus, which is flowing through this capacitor. So now let us see the circuit at time t is equal to infinity. So at time t is equal to infinity, this capacitor will act as a open circuit. And as this capacitor will act as an open circuit, so there will not be any current flowing through this capacitor, or we can say that IC of infinity that is equal to 0. So in this way, found out value of capacitor current at time t is equal to infinity and value of capacitor current at time t is equal to 0, that is 0.5 milliampere. So now we need to find the time constant t for the given circuit, which can be given as R equivalent into C. Now here this equivalent resistance is nothing but the Thevenin's equivalent resistance, which can be seen across this capacitor. So R equivalent is nothing but the Thevenin's equivalent resistance that is seen across the capacitor at time t is equal to 0. So to find this Thevenin equivalent resistance, we need to remove all the sources connected in the given circuit. So this voltage source will act as a short circuit, and hence the R equivalent is nothing but a parallel combination of these 20 kilo ohm resistors. So R equivalent is nothing but 20 kilo ohm in parallel with a 20 kilo ohm, which will come out as a 10 kilo ohm. So our time constant T will be R equivalent into C, that is 10 kilo ohm into C is 4 microfarad. So that will come out as a 40 millisecond. Now the capacitor current IC of t can be given as IC of infinity plus IC of 0 minus IC of infinity, that will be multiplied by e to the power minus t by capital T. Earlier we had found out this IC of infinity is 0 and the value of IC of 0 is 0.5 milliampere minus IC of infinity will be 0 and that will be multiplied with e to the power minus t by capital T, that is 40 millisecond. So we will get 0.5 e to the power minus t divided by 40 millisecond. So that will come out as a 0.5 into e to the power minus 25 t. So this is the equation for the capacitor current for a time t greater than 0. So now let us see the second example. So in the second example, we have given that this switch was closed since a long time, and at time t is equal to 0, this switch is getting opened. And so we have been asked to find the voltage Vx, that is a voltage across this resistor at time t is equal to 0 plus. So as we have been given that the switch is closed since a long time, so first of all let's draw the circuit at time t is equal to 0 minus. That means the time before the switch is getting opened. So at time t is equal to 0 minus, as the switch in the position, and in this position the circuit is since a quite long time, so this inductor will be in a steady state condition. So this inductor will act as a short circuit, and because of this short circuit, this 20 ohm resistor will also get short circuited. So at time t is equal to 0 minus, the equivalent circuit will look like this. So the current that is flowing through this inductor at time t is equal to 0 minus will be nothing but a 2.5 ampere. So value of IL0 minus will be nothing but 2.5 ampere. So now let us draw the circuit at time t is equal to 0 plus. So as we know, the inductor opposes the instantaneous change of current. So at time t is equal to 0 plus also, the current that is flowing through the inductor will be 2.5 ampere, and it will act as a current source with a value of 2.5 ampere. So at time t is equal to 0 plus, the circuit will look like this. And hence at time t is equal to 0 plus, the voltage across this 20 ohm resistor is nothing but minus 2.5 ampere into 20 ohm, that is nothing but minus 50 volt. So we can say that at time t is equal to 0 plus, the value of this voltage Vx is nothing but minus 50 volt. Alright, so now let's see the third example. So in this example we have given that the switch is open since a long time in the given circuit, and at time t is equal to 0, the switch is getting closed. So we have been asked to find this current IT for the time t greater than or equal to 0 plus. So first of all, let's draw a circuit for the time t is equal to 0 minus, that is the time just before the switch is getting closed. So since this 1.5 ampere current is applied to the circuit since a long time, so this inductor will act as a short circuit, and hence the circuit at time t is equal to 0 minus will be look like this. So this 1.5 ampere current is getting divided between these two 10 ohm resistors. So you can say that IL of 0 minus is nothing but 1.5 divided by 2, that is 0.75 ampere. So the current that is flowing through this inductor at time t is equal to 0 minus is nothing but 0.75 ampere. So as this inductor opposes the instantaneous change of current, so this 0.75 ampere current will continue to flowing through this inductor at time t is equal to 0 plus as well. So now let's draw the circuit for the time t is equal to 0 plus. So at time t is equal to 0 plus, this inductor will act as a current source with a value of 0.75 ampere. So the equivalent circuit at time t is equal to 0 plus will look like this. So now if you see here at this node, the current that is going in this side is 0.75 ampere. So out of 1.5 ampere, the 0.75 ampere current is going in this direction. So the remaining 0.75 ampere should get distributed between these two 10 ohm resistors, and the value of these two resistors are equal. So the same amount of current will get divided to resistors. So we can say that this I of 0 plus is nothing but 0.75 divided by 2, that is 0.375 ampere. So in this way we found the value of this initial current at time t is equal to 0 plus, that is flowing through this 10 ohm resistor. So now let us see the circuit at time t is equal to infinity. So again, in a steady state condition, this inductor will act as a short circuit, and hence at time t is equal to infinity, the equivalent circuit will look like this. So now this 1.5 ampere current will get distributed between these three 10 ohm resistors. So the current that is flowing through this 10 ohm resistor at time t is equal to infinity is nothing but I infinity, that is equal to 1.5 divided by 3, that is 0.5 ampere. So this is the current that is flowing through this 10 ohm resistor at time t is equal to infinity. So in this way we found the value of current at time t is equal to infinity and time t is equal to 0. So now one more thing that we require is the time constant of the given circuit. So the time constant of the circuit can be given as L divided by R equivalent, and this R equivalent is nothing but the equivalent resistance that is seen across this inductor at time t is equal to 0 plus. That means the Thevenin's equivalent resistance that is seen across the inductor at time t is equal to 0 plus. So for that we need to remove all the sources connected in the given circuit. So this current source will act as a open circuit, and hence at time t is equal to 0 plus, the equivalent resistance across this inductor is nothing but two 10 ohm resistors in parallel that is connected in series with this 10 ohm resistor. So R equivalent will be nothing but 10 ohm in parallel with a 10 ohm resistor, that is in series with a 10 ohm resistor. So which will come out as a 15 ohm. So our time constant T can be given as L divided by R equivalent, that is nothing but 15 millihenry divided by 15 ohm, which will come out as a 1 millisecond. So in this way we found the value of current at time t is equal to 0 plus and at time t is equal to infinity, and also we found the time constant for the given circuit. So now this I of t can be given as I of infinity plus I of 0 minus I of infinity into e to the power minus t divided by capital T. So it will come out as a 0.5 plus 0.375 minus 0.5, that will be multiplied by e to the power minus t divided by 1 millisecond. So we will get 0.5 minus 0.125 into e to the power minus 1000 into t. So this is the equation for the current that is flowing through this 10 ohm resistor for the time t greater than or equal to 0. So I hope in this video you understood how to solve the problems based on the transient analysis for the RL and the RC circuits. So the more example based on this transient analysis is given in the description below. So you can try to solve those examples by yourself. And if you find any difficulty, then do let me know in the comment section below. And if you want the solution for those problems, then do let me know here in this poll. So if you have any question or suggestion, do let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.